And we're going to try to get this. Now, here's what I do. Turn this off. And go here. Later, bitch. Yoi time. Okay. Hello. Can you see me? Team over there. Let me just check if you can see me. Looks like you can see me. Yeah, you can see me. Okay. I'm going to take my own pill. I lost the other half of that pill. Maybe I took it. I don't know. Hello, team. Can you hear me? I hope you can. Let's see. Just checking to see if, like, you can, if basically if this is visible. I'm logged in as me. I think you can see it. Says it's streaming live. It's been live for a minute. I'm new to all this, okay? So please bear with me. You person in the future who will watch this. Hello and welcome to Fiona time. Right. So I have group meeting in about 40 minutes, so I'm going to try to get through as much of this tutorial as I can. And this is going to be just a tutorial in a series of tutorials that I do so that, so that kind of my knowledge can get passed down to future students. A little bit about me. I was born a baby, a blank slate. No. I have just finished my PhD in the Woodcock Lab, and so now I'm like a doctor or whatever, and it's cool. But now I'm gonna move on to do a postdoc, and so I'm trying to like kind of synthesize all of my knowledge, the vast knowledge I have, into a set of videos that potentially could be watched by future students. So here we are. Here we find ourselves. You, the viewer, and me, the maker of the video. And I hope that this works, because otherwise I'm going to have wasted, 40 minutes talking to a webcam while thinking that this is recording. But okay, here we go. So let's see. So what we're going to do today, and I think you can probably definitely see this over here, is we are going to construct this protein. This protein is the CHARMM. It's known as CHARMM main protease, or 3CLpro, 3-cysteine protease. Who cares? It is the main protease used by SARS-CoV-2, the virus that causes COVID-19. And this protein is important because once the virus enters human host cell and all of the virus's genetic information is transcribed by the human host cell machinery and whatnot, this is one of the first proteins produced. And this protein is responsible for basically breaking up all of the other proteins. So basically the genetic information from the SARS-CoV-2 virus gets transcribed and translated into a giant kind of mega protein that needs to be broken up in order for those proteins to work. And this protein is the protein that breaks up that mega protein. And I think it's quite fun because it looks like a heart. I truly hope that this works, because otherwise I'm just going to have recorded this for nothing. Yeah, so, and you can see too that I've solvated it in a box of water molecules, and this water box is like 110 angstroms long. It has ions to kind of replicate or represent the biological electrostatic conditions. And yeah, so we'll learn how to do this today. And I'll show you how to do it with a kind of ready-made tutorial set. And what did I say? Yeah, I also wanted to change the color of that, but I never did. So let's see. I'll quickly change the coloring method to, what do we want to change it? Secondary structure. That always makes it look kind of pretty. I saw a fun picture where they had changed it to look like rainbow, and that was nice. Happy Pride Month, everyone. It's June 2020 right now. It's like day 1000 of kind of stay at home, safer at home, work from home type situation. Okay, I'll stop complaining. Okay, so we want to build this protein in CHARMM, and as this is like my first tutorial, I'm just gonna kind of go off the cuff, off the riff, and you'll be able to follow along. I have packaged some files to follow along, but hopefully in the future I'll be able to also give kind of more background information into like the theory, into what's going on and everything. But just initially right now, the reason we want to build this structure in, just period, is we want to take the structure that experimentalists have solved and read it into our biomolecular modeling program called CHARMM, so that we can then use CHARMM to simulate this protein in space and time and see how the residues or the amino acids in the protein move and how those movements might relate to the protein's function. That is important just in general. Understanding how proteins move and function is important. Understanding their structure-function relationships is important. In particular, in the case of this protein, we really want to understand how it works, because we want to understand how to make it not work, right? Because this is a protein important to SARS-CoV-2 virus, and if we can stop it from working, then we can potentially basically we do that using some antiviral, and that could serve as an antiviral that would help a lot of people. So yeah, just like no pressure or whatever, just like once you get this set up, like go ahead and just like cure COVID for us. Okay, great. Unless you're watching this and you're like super in the future, and in which case, wow, I wonder how 2020 ended. I hope it ended for the better. I will note that my birthday is November 3rd. And so November 3rd, 2020, there's going to be an election. So if you're watching this post that election date, yeah, wow. Wow, that person really did that thing. Yeah. Okay, great. So this is the end product. How do we get here? So as I mentioned, that what we want to be doing is starting from a structure that experimentalists have resolved or solved using some type of crystal structure from X-ray crystallography, or even a cryo-EM, cryostatic electron microscopy, any type of experimental structure. So we want to start with an experimental structure, and we want to first build it and set it up in a way that CHARMM will understand it, CHARMM being our biomolecular modeling program. And then we want to use CHARMM to simulate it. So let's start there. So if you have this, if this stream has worked, then you probably also have received, shouldn't go on that one. You've probably also received an email from me, including a link to this Google Drive folder. Hope you can see it. And this Google Drive folder contains all the things you will need to do this whole, start to finish this whole tutorial. Okay, so this, if you come here, I hope you can also see my mouse. I think you can. This little file here is the experimentally resolved structure of the SARS-CoV-2 main protease, with a slight asterisk on that. And if you don't understand the following sentence, it's okay. I'll probably explain it in a future episode about homology modeling, but here goes. The solved crystal structure of the main protease for SARS-CoV-2 only came out as a monomer, right? So if we go back to our picture of SARS-CoV-2 M protease, this, what looks like a heart, is actually a dimer of two homomonomers. So these monomers are the exact same, but they dimerize, and the protein functions in this dimer heart shape. So without both monomers, you don't get a functioning protein. So for example, let's see if I can. me learn how to use the program I've been using. Now, you know what? This is just how it goes, team. Anyway, let's change it to color by entry, and then you'll see what I'm saying. See, seg name is right there, chain. Okay, so it's less pretty, but you can see from this picture that the heart is actually 2 rectangular or ovular lobes, okay? And each one of those it then dimerizes to form a functioning protein. But in the crystal structure that experimentalists have solved since SARS has become a problem for, since like whatever, March or whatever, they only resolved 1 monomer. So this structure that I'm using, that I've included in this set of tutorial files here for you, is a homology model of the actual crystal structure of the monomer that has been kind of homology modeled onto the dimer from SARS-CoV-1. So that means they took SARS-CoV-1 structure and essentially aligned SARS-CoV-2 monomers onto that structure, and now have produced a dimer heart-shaped thing of it. The reason I say all of this to say, you could also go, another way to get an experimental crystal structure is to go to the protein data bank, just like this, and then go here, and I think the PDB ID is 6LU. No, that doesn't sound right. Yeah, that's not right. SARS-CoV-2 CLpro. Let's see. So there's more structures, but you could come here, and when you come here, what is it called? Let's just see what happens. No, the original structure was like 6 something. You know what? Let's just go to where I know I have that information. Twitter. Go in my messages. Spike. La 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 la. 6LU7. Okay. 6LU7. So this is the PDB ID that most people have been using, and it's very misleading, because you come here and the structure that they present in this fun little viewer is the dimer, right? So it looks like the heart, but when you save it out, it's only one of these monomers. So I guess they just expect you to align it yourself. But webs, we will work with the structure we have, which is the dimer already, which is great. Okay, so I'm going to show you how to build this with files that I've already generated. You don't have to edit anything. I'm just going to walk you through what the files do. In a future tutorial, I will break sections of the files. I will mess them up so that you have to fix it. You have to debug it yourself. And that is another skill that you'll have to learn. Future person, whoever you are, I don't know who I'm talking to. Okay, so the first thing you're going to want to do to follow along in this fun little tutorial is download these files. And I'm sorry if it suddenly seems like the screen is changing, it's because it is. I'm just switching between workspaces. So hopefully I'm not moving too fast. So I guess you could always pause this, right? Okay, so come here, and what we're going to do is we're going to download that PDB, which we already downloaded, and then what we'll do is we'll download, so I gave you both inputs only, and I gave you complete, meaning essentially this is a complete, I've done all the simulations, so if you get stuck somewhere, you can go see what the answers are, really. So we'll download this as well. Okay, and scanning for viruses. Coincidentally, it's about a virus. Okay, so we'll save it. Okay, and we have the PDB. Okay, great. So The first thing that I do when I have a protein structure I need to prepare for CHARMM is I download the PDB however I've gotten the PDB. So from Protein Data Bank, from a collaborator, whatever. And then I parse it using a tool that we have called CHARMM. And this initial parse just does things like clean up the PDB file itself. Because for example, if I just show you what that PDB that we just downloaded, if I just show you what it looks like, and I already had it downloaded, so I'll just show you the original. So if I show you what this PDB looks like, it's got some remarks up here, so they're commenting, they're providing info about what the structure is, and then they give the atoms and the positions. So also it's important to know that like this is basically saying atom number 1 is a nitrogen, a serine, it's in chain A, right? So A versus B, the two monomers of the dimer, has XYZ coordinates of blah 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 and blah blah and blah, and then it has these other columns which I don't know, and then another reiteration of the fact that it's a nitrogen. That is somewhat important because not all of the atom names always make so much sense. Like Ca, that means C alpha, but I guess it's just reiterating that is a carbon. Okay, but this is just the generic protein data file, whatever. And so what CHARMMing will do is parse this into CHARMM ready files. So, and you could do this by hand, but why do it by hand if you can use a computer to do it? So come here to this CHARMMing website. Sorry, I probably should show you how to get here. So you go www. You just go into your Google bar, charmming.org. Click. I'm already logged in, I guess. Maybe I should try to log out and see, and then redo it. Okay. Let's do that over again. Person. www.charmming.org. Here. I'm back here. Now I need to put in my username, which is already saved, and my password, which is not saved. So this will be fun, seeing if I can remember it. Yes. Thank goodness. Okay. Would you like Firefox to say yeah? Okay. So, and if you don't have an account, I think it's easy to make an account, but if you don't have an account, let me know. Like, I can just give you my account. Okay. Now, we are here in CHARMMing. And CHARMMing is great because you can actually do a lot of the steps that I'm going to show you. You can actually do it basically by button clicking here. Boy, do I hope that this is saving somewhere. Maybe YouTube. Let's see. Let's just give a check on YouTube real quick. So it says it's still going. Excellent connection. Picture in picture. It seems mute. I so hope that this is going, because if it doesn't, then I'm going to cry. But I cry very easily. Okay, I think it's going. Okay. Sorry, guys. Sorry, team. Where was I? Here. Okay. So we're on CHARMMing, and what we want to do is submit the structure to CHARMMing so that it can parse out all of the junk from the PDB and then give us back PDBs that are easy to use in CHARMM through the terminal. Okay, so I'm going to do this. I'm going to submit the structure. Click Submit Structure here, and now it gives you some options how you want to submit the structure. You could actually do this button, and then you just simply put in like a PDB ID, like you could say 6LU7 or 1UBQ or whatever your favorite PDB ID is. But I already have a PDB I want to use, so I'm going to click this button, Upload My Own PDB File, Browse, and we downloaded it, so it's in our downloads, and this is the file name. So we click Open. Okay, so now it's got that. And CHARMMing is also cool because you can like actually do lessons, so it kind of teaches you, which means that what am I doing right now? I don't know. But so you could associate this structure with a lesson, and that would basically get it tagged into the lesson stuff, but we're not doing that right now. We just want to feed it in so we can get out a more usable file format. Okay, and always a good thing to do is click this button, use ProPKA to automatically assign protonation states. So ProPKA is a tool that can help predict the protonation of amino acids in a protein using several different, basically just calculations of the electrostatic environment, the pH, and then different neighboring residues and all of that. It is an approximate method, but it's pretty good. And it's useful because there are a lot of amino acids and proteins that have like wildly different protonation states or pKa's than their like kind of canonical textbook value. So you often want to make sure that those residues are represented appropriately in the structure. So basically, if you have a glutamate, that glutamate should have a pKa, side chain pKa around 4 or 5, but or maybe 3 or 4, I don't know. Look it up in a textbook. But if glutamate in your particular protein actually has a pKa of 8, then that glutamate should be protonated, right? If the pH of the solution that the protein is in is around 7, then that residue should be protonated. So you at least want to know that information. So I always click that button, and most recently when I've done this, it hasn't been working just on the website, but I've already given you the pKa output anyway, so we can look at that. But right, let's move on. So now what you do, click that button and then hit submit structure. Okay, so now it's going to think for a little bit. Okay, and now it's asking us to choose the segments that we want, right? So we gave it a protein structure with 2 segments, a dimer of basically 2 homomonomers. So we want to tell it both because we want both structures. But it's basically saying, okay, we will parse these into separate structures, but do you want both of them or do you just want one? And this becomes important because there's a lot of structures that have many different parts. So like you might have a structure with DNA components in it. You might have a structure with ligand components in it. You might have a crystal structure that contains water molecules. So you, at this point, you can tell it like, okay, I don't want that, or I want this, whatever. In this case, we want both things. So we click those buttons, and I don't usually click this button. So you see it says here, modify protonation states of titratable residues. I will usually do that by hand after setting up the protein on my own. So all I'm using CHARMMing for is to parse the initial PDB. This is gonna take forever because I talk a lot. Okay, so I submitted it, and now that you've defined the physical and chemical makeup of your system, you may proceed to run calculations. Okay, great. But what I started out telling you I wanted to do was I just want to submit the structure to get the structure back out. So now I can already download files. Oh wait, no, not yet. I can't download files yet. What I need to do is I need to trick it into starting an energy calculation so that it sets up the protein, and then I'll download the files from there. But I don't really care about the energy that it's going to calculate. I just want to do this so that it sets the files up. And while it runs, I'm going to have a bit of coffee. I'm sorry. I'm ill prepared to do this job of teaching you virtually person in the future. I hope this is working. Goodness gracious, if this doesn't work, I'm going to lose my mind. Let's check. Armpit check. No. Nothing in there. Yeah. Let me check here. Okay. Looks like it's working okay. Sorry, I just came over to the stream and I see that I'm checking my armpits. Okay. Let me see too, maybe it would help to keep the lighting consistent if I turn these lamps on. Sorry that I'm basically it's still running, so I'm waiting. Probably cut all this out. You guys are like, this is so boring. me see. I'm still trying to ensure that it's working. Live streams. I mean, I think it's working. Your channel videos. I hope it's working. If not, it's okay. I'll just how do I go to YouTube Studio? Let's see if I do this now. Will it show me? Great. Okay, great. Actually, okay. So we didn't need to wait for the energy to completely finish before it gave us what I wanted, which was just these two parsed PDB files. Okay. So again, now after clicking energy and getting it kind of going, we can download these files. I think, oh, if you click the file button, it shows you what it looks like. But then, like I'm saying, is it parsed it. So it gave, I basically set it up in a way that CHARMM is more ready to read it now. So now let's go back to here. If you click the file button itself, then you download it. Save, okay. And save file, okay. Everyone's probably like, Fiona, you should have turned all your notifications off before you started streaming. Like, oh my gosh, team. Ugh. Ugh. Why the hate? Okay, so now we've got the two files that we're ready to start with, and we also downloaded that tar file, did we? So let's go back and make sure we downloaded that. So here we are, and I want to download this. I don't think we downloaded it yet, so let's go ahead and just press download. Scanning for viruses. Scanning for viruses. Viruses. Save file. Okay. And now, let's Control Shift T. Nope, didn't want that. Nope, nope. I wanted a new terminal. Okay, so we downloaded the tar file, right? Because if I click here, basically you should know how to see your own downloads. And this, all of these steps should work except for the following step on all platforms, right? If you're in the internet should work on whatever computer you have. I don't know how to use Putty because it's been so long since I've used it, so hopefully I can get someone to teach Putty if you need to use Putty on a Windows machine. But I'll show you how to transfer files from your local machine, and as long as your local machine has a bash terminal, then you can transfer them to the cluster, research computing cluster. Okay, so I'll get two tabs just in case. So here I am in this window. I am in just my own local computer thingamajig. And now what I want to do is I want to transfer the downloaded tar file to the research computing cluster. So first, let's go to downloads. Now I'm in my downloads folder, and if I do an ls, and again, hopefully I make another tutorial about like bash and all of that, my favorite bash things to do. But for now, I'm just going to click, and if I go too fast, you can always pause or slow me down. It's probably going to be like 5 hours long, so you're probably not going to want to slow me down. Okay, so the first thing we want to do is use something called SCP, that's secure copy. And we're going to securely copy the tar folder, which is called this. So I guess I downloaded it twice, but copy that tar folder to my name at crc.rc.usf.edu, right? So we need to give our username at, and then the research computing cluster thingy, and where do I want it to go? So now I have to tell it where to go once it gets to the research computing cluster. And I want to put it at work BGFS F Fiona Kearns. Okay, so this is the folder I'm telling it to go to on the cluster. Okay, and now it's asking me my password. Okay. So it's going to take a couple seconds. Now it's transferring. Okay, great. So now I'm going to come into the new tab. I'm going to SSH into that place onto the research computing cluster. You guys are all probably like, how did she get a PhD? She is so ill prepared. It's like, yeah, I know, right? She is ill prepared. Okay, so now, sorry, I'm in the research computing cluster, and the thing is, let me just go back. The thing is that when you first log into the computing cluster, you are placed in your home directory. So I want to go to the directory where I copied that set of files. I have about 10 minutes until the thing, and then I'll pause it and come back. And you guys are like, Fiona, that's it. I'm watching this now. None of that means anything to me. And I'm like, yeah, I know. Duh. Okay, so now I'm in the work directory. I'm in the directory where the tar folder is. Okay, so you can see I have all my other, this is hot. I have all of my other work going on in here. So I have the tar folder here, and that's what we want to use. So we can untar it with the following command: tar minus xvzf 3CLpro, inputs only. The X means expand this tar folder, the V means verbose, so it's going to tell you what it's doing each time, and then the Z and the F are like just fun letters that you add at the end. I don't know what to do, but if I was a computer person, I would know. So just imagine I do know, and I gave you the completely correct answer. Okay, so we're gonna expand this folder. Great. So now, if we do an ls, we see we have the original tar folder is still present, and the original tar folder is still present here, and we have a directory that contains all the files. So I can go in there, and I've given you all of the inputs and, not outputs, but the inputs that you need to follow through this tutorial correctly, which is great. I'm amazing. Have you ever met me before? I'm really great. So now if we go into this build directory, we will find that we only have inputs and like CHARMM based files. We do not have the PDBs that we need that we got from CHARMMing. So we also need to get those PDBs. So let's go back to our downloads folder, right? This tab is seeing everything on my local machine, my own home computer. And this tab over here is seeing everything on the computing cluster, the research computing cluster. So let's go back to downloads and let's do this. So if we go back here, we see these segment A Pro PDB and segment B Pro PDB. And now these files, I should also point out, these files are the same as these files. I just happened to download it twice, so it sticks a 1 on the end to make sure I'm not overwriting something. But okay, so I want to send this file, segment apro.pdb, to the research computing cluster. So let's do that. So we can do that by saying scp, again, if we type correctly, scp segment apro.pdb, and then say /, and again, I want to put it in work bgfs f Fiona Kearns, but I also want to now put it in that subdirectory that we just made, which is, now I'm on the tab that's on the computing cluster. So that is work bgfs f Fiona Kearns, then this folder. So that's specifically where I want it to go. So I'm going to go ahead and copy this part and come over here and paste it over there so that it goes to the completely correct spot. Okay, so we're ready to go. And now password. Great. Oh, I could have made this easier by using a wildcard, but, oh well. I'll show you what I mean. Okay, so I have 2 files that I want to copy to the research computing cluster from my downloads folder, and they both have a very similar name, except in one there's an A and in one there's a B, right? There's segment A pro.pdb and segment B pro.pdb. So what I can do to get both, to copy them both at the same time, is just simply put a star there, and that says find all the files that have a name that looks like this and copy them to this location. Hopefully this doesn't do anything terrible. It won't. So, ready, go. It probably will, I think. Huh, we'll see. Okay, great. I hope you can hear me too. Maybe I need to move this closer. Let me just go ahead and move this to where my coffee is. Just so that, just in the event that you can't hear me. I know my voice is beautiful and everyone wants to hear it all day. We're all learning here, team. We're all learning. Okay, great. So now, yeah, it worked. It did exactly what I wanted. It copied the 2 files over to the folder that we wanted them to. So now we're in our computing cluster and we're in that folder we want it to be in. So if we just do simple ls, we now see that we have the 2 files that we wanted and they're in the folder that we want. Okay, so great. Everything's great because now we're on the research computing cluster and we have all the files that we need. Great. So let's just do a quick summary of where we are right now. Currently, I'm in my work BGFS Fiona 3CLpro inputs only build folder. And if we back out 1, we see we have a couple of folders in this directory. We have build, solvation, neutralization. Sorry, you can't see me pointing. Build, solvation, neutralization, heating, and equilibration. And that's the order we're going to do these in. And in each of those folders, you should have all the inputs that you need. The only thing that you'll have to get is the resulting outputs and then move them over to each subsequent folder. Okay, CD, so I'm going to change directories into the build folder again. And let's take a look at just the input folders really quick. So I'm LSing only the input folders, or input files, sorry. Okay, so the first thing we want to do is we need to build all of the segments. Now, in this case, we actually only have an A and a B segment. We don't have waters or ions. So let me go ahead and just delete those things for you so that you don't get confused. And then in the file, I'll update the tar file that's on the directory right now. So I'll remove build waters.imp, remove append watts and ions, remove append A watts, and remove append A, B, C. Okay. It's so hard to be me. Okay, so let's do that again. So let's ls star.imp, altrh, and we see we have 2, nope, we're gonna remove append A and ions. Okay, and now, okay, so now let's take a look at, great. So the only inputs you should have, only input files you should have are these 3 files. And let me go ahead and get rid of remove top, all 36 NA, just to not confuse you. Remove R, all 36 NA, perm to not confuse you. Great. And let me remove, no, we'll keep that there. Okay, so let's take a look at what build A has in it. So this file will take the file that we got from CHARMMing for the A monomer and set it up so that it's CHARMM ready. So the PDB file itself has been parsed, but we still need to write out what's called a PSF and a coordinate file, right? CHARMM doesn't operate on PDB files. It really operates on PSF files, protein structure files, and coordinate files. The protein structure file tells the program CHARMM how all of the atoms are connected by what bonds and what angles and dihedral potentials and all of that. And the coordinate file tells CHARMM where those particular atoms are in space. So I like to think of the PSF file as the list of RSVP'd guests to like a wedding or a party, meaning that like these are all of the guests that are going to be at your party, and this is how they're related to one another, right? But you also need to know the seating chart. You need to know where exactly those guests are in the party, whatever. How many parties do you guys go to? I don't know. But if you think of a wedding, right, you have an RSVP list, a list of invited people that are allowed in the party, and then you have a seating chart where those people will be sitting at what tables, right? So that's how I think of the PSF and the coordinate file. Okay, great. So here we are. Why is that in there? Well, we'll see. We'll check. We'll check. Don't worry. Okay, so if we come to this file, the main chunk of this file is saying, okay, we need to read in the topology file. That's the total topologies of all like protein types of molecules that CHARMM could encounter in the following simulation. So basically this is saying, hey CHARMM, welcome to the world of chemistry. These are all of the types of protein molecules that you could encounter in the following calculations that we're going to ask you to do. So here's another thing, and I hope to like talk about this more in a future episode. CHARMM knows nothing. You have to tell CHARMM all of chemistry every time you start the program. The program is simply just a series of like kind of mathematics that it does. So it knows how to run a simulation. It knows how to calculate force equals mass times acceleration 1 billion times. It does not know chemistry, so it doesn't know how to calculate the energetics required to calculate force, right? Because force is the negative derivative of the potential energy, right? So every time you start CHARMM, you have to tell it, these are the types of molecules you could encounter. That's a topology file, right? So what I'm saying here is these are the types of protein molecules, and these are the types of kind of generic other molecules that you CHARMM could encounter. You have to tell it that. And you also need to tell it, okay, for each of those molecules, these are the bond strengths, bond equilibrium values, angle strengths, angle equilibrium values, dihedral potentials, any non-bonded interactions. You have to tell it chemistry. You have to tell it how these atoms interact with one another. And that's what a parameter file does. And the parameter file, again, comes kind of broken down into a protein parameter file and a generic molecules parameter file. Shoot. The meeting is starting without me. I need to pause. So I'll pause this, and let's hope that I can pause it and not lose everything. So if you're seeing this and I succeeded, go me. But I'll go ahead and end the stream here and then try to fix this later, or finish this later. How do I do this? I'll just end the stream and then start a new stream. Yes, unfortunately, I'm sure.